In the last video, I said that the value of a function near a known reference point can be found with the following infinite sum, called a Taylor series. I said that if this reference point was at x is equal to 0, we call it a Maclaurin series. The binomial expansion is the Maclaurin series for the following function, 1 plus x to the power of n, where n does not need to be an integer. Our reference point is x is equal to 0, and this first term is found simply by evaluating the function at the reference point. X being equal to 0 leaves just 1 inside the bracket, and regardless of what n is, raising 1 to its power will result in 1. Next, we need to find the x coefficient. Differentiating 1 plus x to the n is done using the chain rule. We get an n out front, and the power is reduced by 1 to n minus 1. We must evaluate this at the reference point, x is equal to 0, which again results in a bracket term of 1. The coefficient is then just n. The 1 over 2 factorial is multiplied by the second derivative, evaluated again at x is equal to 0, to form the x squared coefficient. This process is continued, and the resulting series is the following. This is what we call the binomial expansion. That means that the value of 1 plus x to the power of n at some x value near to the reference point x is equal to 0 is given by this series. I will say without proof that this series is valid when x is between minus 1 and 1, or when the modulus of x is less than 1. This makes sense since if x were greater than 1, each of these ascending powers would get larger and larger, resulting in an infinity which we don't want. Given this expansion, we can easily find the expansion if the x in the bracket were to be replaced by some function of x, let's say 3x. If we change the argument, all we need to do is replace all the x's with 3x's. Notice also that the x in the domain also changes to a 3x. It is the function of x that must have a modulus of less than 1. The final and most general case is if the first term in the bracket isn't 1, for example, it could be 6. We want to factor out this 6 so that the coefficient is again 1, and we can use the series. We factor it out within the bracket, and then use this rule of indices to express it like this. The bracket term can now be written using the binomial expansion. I now want to talk about the case when x is an integer. Start with expanding out this bracket starting from n is equal to 0 and working up the integers. If you look at the coefficient, you see what is called Pascal's triangle. Each number in this triangle, other than the 1 at the top, is the sum of the numbers directly above it. This triangle extends for as long as you like. We see the series looks very much like what we would expect from the binomial expansion. For example, with 1 plus x to the power of 5, we would expect the first 3 coefficients to be 5, 10, and 10. We would hope that these two expressions are the same, since we think both are correct. But why is this one not an infinite series? The reason is that because n is an integer, when we count down from n to n minus 1 to n minus 2 and so on, we will eventually reach 0. With n is equal to 5, it looks like this. This 0 term is present in all further coefficients in the expansion, and so all of these will disappear. Coming back to our general expression, where n doesn't have to be an integer, notice that the closer x is to 0, the smaller each of the progressive terms are in the expansion. If x gets close enough to 0, each successive term becomes so much less significant that we can estimate the value of the whole series by just a few terms at the start. For example, here if we set n to 1/3 and x to 0.1, we would be looking for the value of 1.1 to the power of 1/3. By using just the 3 terms in the expansion, with n is equal to 1/3 and x is equal to 0.1, we get this result. The result of 1.1 to the power of 1/3 in our calculator is this, and we can see just how accurate the 3-term estimate is. This is a way of estimating the powers of any number close to 1. For example, to estimate the value of 0.94 to the power of 5/6, you must only set n to 5/6 and x to negative 0.06 and use a few terms in this binomial expansion.